Hey there, awesome physics students. Let's talk about Poiseuille's equation. This is a nice French name there. This is an equation that tells us how pressure differences drive fluid flow. Before we get into the nitty-gritty of that, I want to remind us of our cause and effect relationship paradigm that we talked about before. So we have cause here, and that produces an effect. But then we always have a property in the middle. And so, and I want to add another thing. This is a law that goes with this cause and effect situation. So the first cause and effect that we talked about is that forces cause accelerations, but not all forces cause the same accelerations. It depends on the object, specifically the property of the object, the inertia that is characterized by the mass. And the sum of I'm going to write the law that connects these three, is that the force is equal to mass times acceleration. Of course, it's the net force, but that's the connection between these three, the cause, effect, and the property. There's also the torque, which causes angular acceleration, alpha, changes in the rotational state. But then there's a property in between that we call the moment of inertia, that is the rotational inertia. How difficult or easy is it to get things to change their rotational state. The equation that connects these three is very similar. We have the cause is equal to the property times the effect. Finally, I want to introduce to you a new one that is from Poiseuille's equation. That is the cause-effect property paradigm. The cause that we're going to talk about is pressure differences. So this is a difference in pressure from one end to the other. So let me just draw what this looks like here. The idea here is if you have a tube and the length of the tube or pipe or circulatory system, a blood vessel or something like that, has a length of L, and the radius of this is R, and there's going to be a fluid flowing in this, and we're going to have a pressure on this side, a high pressure on this side, and a low pressure on this side. And that's going to drive fluid to flow through it from high pressure to low pressure. So when I say delta P, I'm saying P high minus P low. All right, so that's the thing that drives this fluid through here. What does that cause? That causes fluid flow. Fluid flow is going to be, if you recall, we used the symbol Q for that. That's the volume that's passing a certain point per time interval. Okay, so this V here is a volume and not a velocity, just to be clear on that. And we also use the letter Q for that. But there's a property in between. And as you can imagine, the property in between depends on the properties of the fluid itself. So eta is going to be in there. The length is also going to be in there. If you're going to drive fluid through a larger length, that's going to take a bigger pressure difference, because the resistance of this, which is the characteristic that we're going to have, the property in here is the resistance of this. The resistance is going to increase if we increase the length of this tube or pipe. And then the other thing is the thickness of this pipe, or the fatness, right? And so that's characterized by the radius here, which tells you about the area that it's traveling through. And so a bigger radius will decrease the resistance, and so that's going to go on the bottom. Now there's going to be some constants that are in here as well. So there's an 8 up here, and I'm not going to get into the details of these. And then this R is actually to the 4th power. So that makes the radius of the tube, if it's a circular tube, extremely important in determining the resistance of this. So this is what I'm calling the resistance term here. And it, of course, follows the same paradigm. Otherwise, why would I have brought it up? That is, the pressure difference gives you the resistance, is a product of the resistance, which I'm going to call 8 eta L over pi r to the 4th. That's the resistance term, times the effect, which is the flow rate term here. That's going to be the volume flow rate, the volume passing point per time. And again, this is V is not a velocity, it is a volume flow rate. So this is going to be measured in meters cubed per second. And this pressure difference is again the high minus the low. Okay, so this is the idea behind Poiseuille's equation. It's useful when you're thinking about Poiseuille's equation to just think about these terms separately. So this is the pressure difference. Okay, what affects the pressure difference? This is the resistance term here in the parentheses here. So think about individual changes to the resistance and whether that makes the resistance go up or down. And then finally, what happens to the volume flow rate as a result of that, okay?